This is Game AI Uncovered. My name is Paul Roberts, and in this video we're going to be looking at reactive behaviour trees, with a link to the original chapter in the description below. To kick things off, we're going to take a look at the architecture for this approach. So, we have AI systems, and these plug into our agents. But in a reactive behaviour tree architecture, an agent consists of a couple of components. It has a reactive behaviour tree component and a monitor component. The monitor listens for events and determines how the agent will respond. We will be looking at each of these in some detail, but before we do, let's take a quick look at a standard behaviour tree to see why you'd want to use the reactive behaviour tree approach. As an example, let's build a behaviour tree for a soldier to patrol. We start with the root node, which has one child, a selector. This selector has two children, the first of which is a leaf node that updates the locations the agent needs to visit on their patrol. The second child is a sequence node that requires the agent to set the patrol location, move to it, and then wait for the next position to be acquired. An important component is the blackboard. Each agent can have their own blackboard to store relevant information. For this example, this could consist of a patrol list and the current patrol location. Our leaf nodes can write to the blackboard or read from it depending on what they're trying to do. All good, right? So let's remove the blackboard for now, but be aware that it is there and being used to store the information our agent needs. With this tree, what happens if our agent spots an enemy? Well, we can cater for this. We can add another sequence node that will allow our agent to move to the target and attack. Remember, a behaviour tree works from top to bottom, left to right, so if we want the agent to handle the spotted enemy, it needs to be on the left of the other options. And this highlights the problem with behaviour trees. Is this still a patrol behaviour tree? Not really, it's a patrol and attack behaviour tree. And this is very simple. Imagine all the other scenarios that this behaviour tree needs to handle for a soldier to appear intelligent. Reactive behaviour trees were developed to handle this and return behaviour trees to their simple single purpose intention. So let's take a look at the reactive behaviour tree component, which consists of two elements: single purpose behaviour trees and reactive stacks. A key part of reactive behaviour trees is that the trees do one thing. As we just saw, it is very easy for a behaviour tree to morph into something more, and before long you have an unwieldy tree to deal with. So, jumping back to the patrol behaviour tree we had before we added the attacking behaviour, this is a single purpose tree. It does one thing. It is a patrol behaviour. Reacting to an enemy is something that the architecture will handle. It does this through the use of reactive stacks. The architecture consists of two stacks, a long-term stack and a reactive stack. The long-term stack holds behaviours that are the long-term objectives of your agent, such as patrolling for a soldier, and the reactive stack holds reactive behaviours. For this step through, I just want to get across how the stacks work in the architecture, so we will be using generic names for the tasks. There will be another example later when we have all the concepts down. So, we have a default task on the long-term stack, and this receives the update. Then our agent responds to some event in the world and pushes a reaction task onto the reactive stack. This now gets the update, and the default task becomes dormant. In fact, if there are any tasks on the reactive stack, the long-term stack becomes suppressed. There is no need for us to even look at it whilst we're processing reactive behaviours. Our agent then receives some stimuli from elsewhere and pushes a reaction onto the reactive stack. This now gets the update and the previous behaviour becomes dormant. A third reaction is triggered, which gets added to the top of the reactive stack. Again, this now gets the update and all those tasks below it on the stack become dormant. When the agent has fulfilled the criteria for the topmost behaviour, it can be popped off the stack, and the behaviour at the top of the stack now gets the update. This gives our agent an element of memory. The agent knows what they were doing and returns to that behaviour. You can also clear an entire stack if needed, meaning the long-term stack is no longer suppressed and we return to our default behaviour. You may be wondering what this has to do with behaviour trees. Well, if we move our reactive stacks up to the top and bring back the patrol behaviour tree, this tree is our patrol task, which can be our default behaviour. You may also be wondering what the point of the long-term stack is if it only has one behaviour. Well, it doesn't have to. This stack is for the long-term objective of your agent. Imagine the blue default task is a sniper task, but then you want them to go on patrol. The yellow task could be the patrolling behaviour, and at some point we can pop it off the stack and go back to our sniper behaviour. As with the reactive stack, the topmost task gets the update, and those below fall dormant. But if a reaction gets added to the reactive stack, the whole long-term stack gets suppressed. The final component in the reactive behaviour tree architecture is the monitor. A monitor is archetype specific, meaning you have a monitor for each type of agent in your game. It is this monitor that determines how an agent will react to stimuli, and one type of agent will probably react differently from another. So, the monitor consists of a list of stimuli and the appropriate reaction. The stimuli can come from gameplay systems, remember the monitor listens for these, or from reactive behaviour trees themselves. So let's look at a simple soldier example. If our agent hears a gunshot or explosion, the monitor determines that the soldier should go and investigate, so an investigate task will be pushed onto the reactive stack. If our agent spots the player, the monitor determines that the soldier should attack, so an attack task will be added onto the reactive stack. If our agent revives their health and they are in the take cover task, the monitor determines that the soldier should no longer be hiding and the take cover task should be popped from the reactive stack. If we compare this to a monitor for a sniper archetype, you can see that when a sound is heard, they do not respond. It would look daft if our sniper got up to investigate rather than staying hidden. Unless, of course, that's the behaviour you want for your game. That just about covers how the reactive behaviour tree architecture works, so let's step through an actual example. We're going to use our soldier again, who has a long-term task of patrolling. But then a sound is heard, which comes from our gameplay systems. Our monitor determines the response, and an investigate task is pushed onto the reactive stack, which now receives the update. Whilst investigating, our agent spots the player, so the monitor determines that we should attack. An attack task is added to the reactive stack. This now receives the update. Unfortunately, our soldier has taken too much damage, so our monitor responds by pushing a take cover task onto the stack. This is now the topmost behaviour and receives the update. Once our health is recovered, our behaviour alerts the monitor, which determines the take cover task can be removed. Our agent remembers that they were attacking the player because it is now the topmost task. Unfortunately, our soldier runs out of ammo. The monitor determines that the best course of action is to take cover again. When we've reloaded, the monitor has decided that we should be attacking, but we already have an attack task on the stack. In such a scenario, instead of adding duplicate tasks, those tasks blocking us from attacking should be popped. During the fight, the player has managed to get away, meaning the soldier no longer has a target stored in their blackboard. The attack task can pop itself off the stack, returning the soldier to its investigate task. But no target is found, so again, this task can be removed itself, and our soldier returns to its long-term task of patrolling. Obviously our soldier could have attempted to sound the alarm or some other behaviour, but that's the beauty of the monitor. Allow the designers to decide what each agent should do. We just need to worry about the how. But that's it for this video. This has been Game AI Uncovered. Thanks for watching. Before I sign off, if you have an interest in Game AI, check out these books. Artificial Intelligence in Games will get you up and running with the step-by-step code guides, and the Game AI Uncovered series is filled with insight from professionals about how they did the AI for the games that you love.